Good afternoon. Welcome to the Embedded Executive Podcast. My name is Rich Nass. I am the Executive Vice President of Open Systems Media. I lead the Embedded Computing Design team. My embedded executive for this week is Daniel Callan, a Senior Manager with Infineon. How you doing, Dan?
Very good, Rich. How are you?
I'm doing great. Thank you very much for asking. So the reason I really desperately needed to have you on the call today, something crossed my desk that I need some education. An isolator family that you guys announced, that I'm sure I'm going to get this wrong, but it's the way I got it was that there's no power supply needed. Now, my engineering background says you got to have a power supply. So where am I going wrong here? What did I mess up?
Yeah, it's a great question. So the reality of it is the isolator that we're launching has a embedded coreless transformer. So it isn't that it doesn't need a power supply, it's that it doesn't need an isolated power supply. So we can transfer enough energy from the input side of the product to the output side in order to power our MOSFET, IGBT, CoolMOS family of products without an isolated power supply.
Now, I would think you'd be doing that with super caps. Am I right?
Well, that's actually a really good question, because we actually have the ability on the output side to charge a cap from the input, and it actually gives us more energy to power the MOSFET, so we can actually do a much faster and a higher energy in that isolation barrier for the switch. So for example, in our what we call our standard turn on, we can actually transfer about 185 microamps of energy that can be utilized for the switches. We have a fast turn on feature that has an external buffer cap on the isolated side, and that actually pre-charges through that energy being transferred across the barrier, and then once it's needed, it can be released into the switch. So you can actually have up to 400 milliamps to turn on the switch. So it gives us the ability to switch a lot of different switches, if you will, MOSFETs, IGBTs, etc., on the output, and gives us the ability to really apply to a lot of applications, a broad base of applications.
You read my mind. What are the applications that we're using this for?
So the main applications, our target applications, are solid state relays and AC and DC power distribution applications, industrial automation, so PLCs, for example, programmable logic controllers. Also very similar to the programmable logic controller would be a commercial HVAC controller. So you would use the switch to turn on pumps, fans, things like that, both in a manufacturing environment as well as a commercial HVAC system. And then also battery management systems, so solar inverters, e-bikes, things like that, we can also see as applications. We're finding that even though those are our target application, it's actually finding its way into a broad set of applications across the board. So any time you need a switch, whether it's an electromagnetic relay or another type of switch, you could use this family.
So I get the battery powered application, but in an industrial setting where power is not really an issue, why is this important?
Basically, it's a reliability issue. So when you think about a manufacturing environment, for example, or in high use applications or remote applications, what we're doing mostly is replacing electromagnetic relays. Electromagnetic relays have moving parts, so they have contacts that degrade over time. Sometimes the contacts can break, and that can become detrimental in a industrial environment or in a building automation environment. So the solid state relay that you create from the isolator and the MOSFET gives you a much higher reliability in your end system. So that's the real value.
But what are you actually doing that hasn't been done for? Because solid state relays are not new.
Correct. So solid state relays aren't new, but the advantage that we have over solid state relays, for example, is with that energy transfer that I was telling you about, we have the ability to drive our very low RDS on MOSFETs, for example. So the power dissipation compared to what's currently used, a photovoltaic isolator along with an SCR or a triac, we have much, much, much lower power dissipation. So it's a game changer in terms of the reduction in the board size due to the heat sink. The heat sinks are much, much smaller. So there's a lot of value there.
Smaller, can you quantify?
It's about, say, it depends on the application, of course, depends on what switch you're using, but we've got folks that we're working with in the industrial space that are able to reduce their heat sinks by up to 80%.
Wow.
So it's substantial.
Yeah, that's definitely substantial.
It's substantial.
And what's the competition doing in this space?
Well, as I mentioned, so our key competitors at the moment are electromagnetic relays, number one. Number two, photovoltaic and these SCR triacs that are used heavily in industry. That's another one. And then we have competitors that are actually building similar products. They have less energy transfer and less isolation capability. We're able to meet UL 1570, 1577, which gives us a very, very high isolation voltage. So I think we've got a really, really good product on our hands. It's very value differentiated.
Now, don't take this the wrong way, but this doesn't seem like rocket science. What took you so long, and why isn't anybody else doing it?
I think you're going to see other people maybe try to do it. I think we've got at least one competitor that is doing something similar. I think the other thing that I haven't mentioned yet is, we've also got, if you think about Infineon, we have world-class switches, our CoolMOS S7, our IGBTs, and when you match that with an isolator, you've really got a great product. But what we're also able to do with this product is we've integrated overcurrent protection, over temperature protection, Miller clamping. So Miller clamping is to keep you from, in a noisy situation, if you've got a noisy environment, you don't want to turn your switch on inadvertently. So the Miller clamp helps keep you from doing that. The overcurrent, over temperature protection, again, are system level protection, but also switch level protection as well. So again, further increasing our reliability of not only the system, but the switch itself.
Very interesting. You didn't touch on the cost part. I know you're eliminating some other components, so we're going to talk about this from the system level.
Right.
How do we talk about this from a
yeah? So one of the things that I've been actually promoting, not only within Infineon but to our lead customers, is what we call cost of ownership. So if you try to compare an electromagnetic relay to a solid state relay almost always is more expensive. There are certain things you can do, as we talked about earlier. You can reduce, the components on the output to get your costs down, a little bit, but you really need to look at it in terms of total cost of ownership. So total cost of ownership would be the board size with that heat sink, that big heat sink that you've got to have. That's your system. You got to look at it from a system level cost point of view. Look at reliability. So if you're in a manufacturing environment and you're pushing out a lot of product, you're trying to get stuff done, and then all of a sudden you have a breakdown because the relay failed, that's a big problem and it's expensive to replace. So what we're trying to show our customers is to think outside the box a little bit, beyond the component cost itself, and look at the solution cost and look at the system level cost as well. So the protection that we've included helps in that regard, the reliability, and then just the board level cost, the fact that we can reduce the size of the board itself. So those are that's the way I try to get the customers to think about cost.
So what about availability of these parts, Dan?
They're available now. So you can go to Infineon.com/SSR and you'll find them.
Awesome. I'm going to go check them out. Thank you very much for your time. This has been great.
Great. I appreciate your time very much. It was my honor to represent Infineon, and I really appreciate your time.
My pleasure. That was Daniel Callan. He is a senior manager with Infineon, and I'm Rich Nass with Open Systems Media.